This is the inaugural episode of Two Sides of a Paper. The purpose is to provide an interesting and enjoyable way to keep up on important literature. While it is possible to have a traditional paper review, in some cases, having a form of debate about the paper can be both more entertaining and may better elucidate key points. I will note here that the people describing the strengths and weaknesses of the paper were assigned the side, so they may not necessarily believe the points they are making. We also recognize that all papers, including ones that we have written, have both strengths and weaknesses. Our goal is not to put down the authors or make it seem we are smarter than them. Our goal is to promote a better understanding of the state of science. AI applications in healthcare and radiology in particular have become a major thing. We are familiar with all the excitement, and some have even proposed that it will be so powerful that AI will replace physicians. While that is a debate for another time, it is important to understand the trajectory of AI and its use in healthcare and medical imaging. The paper we are discussing today attempts to describe what the authors perceive as the likely future for AI in medical imaging, the challenges that AI is likely to face, and what should be done about it. In particular, there is a choice in strategy in dealing with images and applying machine learning. Should one extract and use features in an intentional way, reflecting our understanding of what is important in those medical images? Or should we allow and expect that deep learning methods can better identify the features that are most informative? The implications of the answer to this question are profound and would likely result in potentially significant changes to the way many researchers, companies, and regulatory agencies view deep learning in medicine. Taking the side of deep learning, finding the important features, is Shahryar Faghani, and taking the side of intentional use of radiomics is Bardia Khosravi.
Radiomics is the field of extracting high-dimensional quantitative data from radiologic images. There are two general approaches to radiomics analysis. First, using handcrafted features, and the second is using deep learning-based feature extraction. Handcrafted radiomics features are calculated using some mathematical formulas from a predefined region of interest of an image. So one has to first delineate those areas, like the tumor area, and then run a radiomics feature extractor. These features quantify some of that region's characteristics, like shape or contrast, compared to the surrounding area. Finally, most relevant features can be selected from this high-dimensional data and then used to predict patient's diagnosis or outcome. I believe these handcrafted features can be sometimes more useful compared to the deep learning-based counterparts because, first, as we provide the regions to the model, these features are only extracted from that region, meaning that we're at least sure that the final model is looking at the same place. In contrast, deep learning models are very good at shortcut learning, meaning that they can pick up on biologically irrelevant features that will correlate with the final outcome and does not have a biological meaning. For instance, it has been shown that deep learning models can detect the imaging unit as a surrogate for femoral fracture, meaning the radiographs from the emergency department are more likely to have these fractures compared to those taken at an outpatient imaging unit. So the model uses the imaging unit as having fracture or not having a fracture. Second, at least some of these features, especially the shape features, can be very easily explained, and hence decreasing the black box nature of machine learning models. Finally, the most important reason that I have is that these features are standardized. In 2020, a multi-institutional initiative called Image Biomarker Standardization Initiative, or IBSI, was formed to create a consensus across different quantitative radiomics packages to have the same naming and calculation conventions. For example, if two teams report that the gray level size zone matrix, or GLSZM feature number 12, was important to discriminate benign versus malignant lung nodule, then a reader can be sure that they're talking about the same thing. This can be very important as the results from different studies can be pulled and analyzed with greater granularity in systematic reviews and meta-analysis.
deep learning is a targeted trial and errors that will find the best features that are useful for describing a phenomenon, as opposed to radiomics that uses a set of predefined features that doesn't behave adaptively on the problem that we want to solve. As an analogy, imagine that we want to open a lock. Then radiomics would be a predefined set of keys and you need to try different keys. If lucky, then you might open the lock, otherwise you will fail. However, deep learning would be a locksmith who can design a key based on the lock. In radiomics, as Bardia said, segmentation mask of the region of interest is needed, which has two caveats. The first one is obtaining a segmentation mask itself, which needs human experts annotation, thus a lot of effort, or training another machine learning based model for segmentation. Since the quality of extracted radiomics features highly depends on the mask quality, users should make sure that the segmentation masks have high quality, which again needs human inspection. The other downside of using segmentation masks is that you're limiting yourself to the region of interest. However, in biologic systems, surrounding environment most of the times plays a crucial role in regulating the biologic processes. For instance, in radiogenomic tasks, where we're interested in determining the status of a particular gene, or when we want to predict the risk of tumor progression, the surrounding connective tissue and basement membranes play essential roles. As a result, there might be a lot of information outside the segmentation mask that radiomics would miss. To Bardia's last point, although interpretation maps have some limitations, but usually they can provide some insight about not what, but at least where the model is looking at. In other words, still with deep learnings, we can partially provide some explainability. In addition, even on the same problem, selected radiomics features vary based on the selected model. As such, the features are not necessarily reproducible.
Thank you for that presentation. An important question is whether the features that are found by deep learning approaches and radiomics approaches are similar or comparable, and how might we accomplish that?
Well, by using interpretations techniques like interpretation maps, I think we can figure out where the model is looking at. And since some of the radiomics features are morphologic features, so basically the interpretation maps will allow us to find a way to compare these morphologic features. In addition, there are some other interpretation techniques that allow us to figure out the importance of each feature in model's decision-making process. However, the current interpretation maps doesn't provide a way to figure out what the model is looking at.
Okay. A challenge is always getting enough data in order to train models. Is there a difference in the number of subjects that's likely to be required for a radiomics model versus a deep learning model?
Well, as the formula for calculating the radiomics features in traditional packages are already defined, you can extract feature from only a single image. But the point is, after that, you have to run feature reduction dimensionality reduction algorithms and feature selection algorithms and classifiers to just reach to a decision to see if a certain feature is correlating with your diagnosis or prognosis. But in general, saying in published papers, most of the times, the radiomics-based feature extraction works have less number of subjects compared to deep learning models.
Great. And then finally, is it easier to train a model using radiomics approaches or a deep learning approach?
So, in my opinion, training a deep learning model is much easier since it doesn't require any segmentation mask, heavy pre-processing pipeline, or any feature selection process. So,
on the other hand, I think radiomics doesn't have that much of hyperparameters that deep learning models have. So you can reach a properly performing model with less hyperparameter tuning and less playing with the model. But as Shahir said, having a robust segmentation pipeline is always a challenge.
Great. Thank you so much. We hope that you found this discussion useful. Again, in science, there are always two sides to an important question, and we think that there are a lot of important questions out there. And so We look forward to presenting more papers in the future where we will present two sides of the paper.